Thank you very much, Ruben. Thank you very much, everyone, for being here, especially last session of Big Data Spain. You must be all very tired. And for that reason, I'm going to try to be very brief. Not only for that reason, because I think it also makes sense for you to make questions, as many as you have. So today I'm going to talk about data flows. Data flows are arguably the main abstraction behind big data technology today. So you pick any database that you want, and you will find data flows when you look at the query plans that represent the queries that users write. You pick any processing engine that you can imagine, and they are all implemented around the concept of data flows. And there are two good reasons for this. I mean, data flows are simple. It's a simple abstraction that shows easily to users how they could parallelize their computation. And there's been lots of evolution if you think about how data flows have changed in the last decade. So when you think about MapReduce, you have map tasks and reduce tasks, and that's it. But then you see how the research world evolved in this sense, how Dryad appeared, and today we have Spark that picked up some of those ideas and effectively generalizes the data flow model. So despite this evolution, I think that there are many challenges yet to solve. And today I want to focus on one that I consider particularly interesting, and that is the one of the programming language. So how should users write queries? How should users write programs to run in these platforms? And I believe that there's a lot of value that is still to be gained, because when you think about these frameworks that exist today, these were developed by software engineers for software engineers. And the idea here is, hey, it's not only software engineers that have good ideas, that have questions about the data, it's also the scientist that is writing a simulation experiment for a new physics experiment. It's also the marketing representative who knows which data he needs to know to optimize the next campaign, for example. So I will start saying that big data needs democratization. And what do I mean by that? What I mean by that is that it's no longer developers and DBAs that generate, process, and analyze data. Instead, we have lots of different decision makers. There's domain scientists, application users, journalists, crowd workers, everyday consumers. You name it, everyone has data. Actually, many of these people have very interesting questions to do to the data. The problem that we find is that not all of them know how to write those queries. So if you're a software developer, fine. You can pick up Spark, you can pick up Stone, you can learn the new technology, you can write your queries, answer the questions that they make you, that's great. But what does happen when someone that has actually interesting ideas, interesting questions, cannot write queries? So he goes to the local expert. And what happens next is something like the following. So imagine that we have here this scientist that has written this simulation experiment, has got a lot of data. He now wants to analyze that data. He goes to the local expert and says, look, I wrote this script. I just need to run it now on those old machines that have run my experiment. So there's a negotiation process here saying, OK, well, come in 3 days. I will have your results. The guy says, well, this is actually very urgent. Can you have it for tomorrow? The local expert will go on. Well, this is very difficult. You know, we have lots of difficult technologies and names and buzzwords. You name it here. So you have to come in 3 days. The thing is that there's a barrier here. There's a barrier that comes from the fact that there is human interaction, and there's obviously the whole different challenges that you find when you need to communicate your ideas to other people that might be speaking in a completely different language, right? So this is the reason, this is the main problem that I see when I say, hey, we need to democratize big data. There's no adequate interfaces for Bob, in this case, to write their queries. So there is this quote by Ludwig Wittgenstein that says, the limits of my language mean the limits of my world. I truly believe in this quote. I think that if we don't do anything to improve our programming languages today, or the programming interfaces that we have, we are constraining a lot of people to not write questions that, on the other hand, they are very interesting. So that's why I think that the first step to democratize big data would be to offer a familiar programming interface. And I'm not talking about a single programming interface. There might be many. When I say familiar, it's familiar for the specific use case. And today I'm going to focus on the case of domain scientists. So these are people who usually know how to write MATLAB code, or C++ code, Java code. They know how to write their programs, their algorithms in these languages. What they don't know how to do is, or they don't have the time to do, is to get Spark or any other new technology that comes out, learn it, and then write the queries there. So I'm going to follow this outline today, and I'm going to start with this example that I've mentioned. So let's imagine that we actually want to offer a programming interface that is just writing Java code. And for that, I'm going to start motivating the problem with an example of a recommender system. So imagine that you are Amazon or you are Netflix, and your boss comes and says, hey, you have to write a recommender system because I want to, for all the users that I have, to recommend different items. So in the case of Amazon, that might be books or DVDs or everything, really. In the case of Netflix, it might be movies to watch. So to do that, the user will say, OK, well, I will need a user item matrix that keeps all the users that I have in my company and all the items that I have, the population of items I have. And what I'm going to do is I'm going to keep a rating that each user will provide for each of those items. So if user A says, hey, I really like this movie, I will give it a 4. We assign that 4 for user A rating item A. And then we also will have a concurrence matrix. So this concurrence matrix is basically an structure that is going to give us the feeling of the intuition of saying, hey, this given item co-occurs this many times with this other item. So you can imagine if we have 10 users and 8 of those users have bought both milk and bread, we will have milk and bread co-occurring 8 times in this case. And the intuition behind this whole algorithm would be something like, if I have those 8 users that have bought both milk and bread, and I have a new user that buys milk, probably my algorithm should recommend him to buy also bread, because the other people have done that. So without getting into the details of whether this is successful or not, and things say that it would be in the case of Amazon, let's just see how we would implement that. So we have those 2 matrices there, declared as simply Java state, Java attributes. We will need a function to add new ratings. So when a new user comes to my site and says, hey, I want to rate this new movie with a 5, we will just implement that function that gets the row for that user and updates both the user item matrix and also the concurrence matrix. And obviously, I want to provide recommendations. So when I have a new user and I want to give him or her a recommendation, I will just get that vector, and I will multiply it by the concurrence matrix. And again, the intuition here is, by multiplying that vector by the concurrence matrix, I'm going to get a new vector where all those items that have a higher value are those that I most likely will want to recommend to the user. So when you see this algorithm, which is a non-trivial algorithm, and it's not just counting words, we see that we've really expressed it in a very concise way by using that state, right? So mutable state is really good because it leads to concise algorithms, but it complicates parallelism and it complicates fault tolerance. So imagine that now, of course, you go to this same person that implemented this code, and you say, well, now this thing actually has to run on my whole user base, and I have 300 million users. The guy says, hey, well, I implemented the algorithm, now this is somebody else's problem. And why is that? Well, because if those matrices start growing large, we have a problem. We have to probably start thinking about distributing our computation to aggregate the throughput of different machines. And that means that there are going to be failures. In distributed clusters, there are failures. So if there's a failure, and we are keeping that state that allowed us to maintain this code in this concise way, we have to do something to not lose that state. Otherwise, we'll get wrong results. And we will need to manage that state somehow to support data parallelism. So how do other systems do this today? Well, when you look at them, they actually avoid mutable state. They don't have mutable state. And that's a good decision in the sense that it simplifies fault tolerance. I will argue it's a bad decision if you want to optimize or if you want to improve the programming language, because it effectively will constrain how we need to write these programs. So think about MapReduce. It offers you this interface, simple interface with MapReduce task, which is really good for them to implement automatic fault tolerance for the users, but you actually are constrained to write all your algorithms in that form. Twitter Storm doesn't have any support for state. When you think about Spark, they have immutable RDDs. As the name says, they are immutable. You cannot mutate that state. It's not really state. And these are also meant to be updated in a coarse-grained fashion, not like the fine-grained mutability that we expect when we write just a Java program. For example, when we are updating a given item for a given in a given matrix. So what's our approach for this? Or what's the outcome of this discussion so far? Well, programming these distributed data flow frameworks is difficult because it requires learning new programming models. And if we recall what I said at the beginning, we actually want to not require that for our users. We want to say to the domain scientists, you just can write Java code and we will be running it for you. So what's then the goal of the talk? We want to run Java programs that have mutable state, but with the performance and the fault tolerance of distributed data flow systems. And to do that, I will introduce stateful data flow graphs, which is a new abstraction that specifically introduce distributed mutable state in the data flow graph. So those are the red squares, the red diamonds that you see there. I will also talk about some annotations that we provide users so that they can help us with the translation of that Java program on the left-hand side to the SDG in the middle. And I will then talk about how we deal with failures, how we recover state if there's a machine falling down. So I will talk about the checkpoint-based fault tolerance mechanism that we use to recover state when there's a failure. So I will start explaining what's the abstraction, the main abstraction that we have. This is stateful data flow graphs. And the main insight behind stateful data flow graphs is that they explicitly separate processing from data and from state. So when you look at this picture, we have what we call task elements, which are the circles there that represent the computation that you do on data. The edges in the graph are data that is carried from one task element to the other. This is just simply as you would say in a normal data flow when you look at it. The new thing here is that we have those red squares, which are state, that now is explicit in the model. This would be the model, of course. Now, how do we execute this? How do we actually put this in a node of physical, in a cluster of physical nodes? So what we do for execution is we materialize those task elements into physical machines. And for performance, we want each task element to always access state locally. So that's good because, well, you're accessing state locally. If that's in memory, that's fast. But it has a big challenge, which is, hey, if you've given me this model that it seems easy to parallelize because everything is kind of separated, but now I have a task element that is accessing some state. And for a reason, I want to scale out this task element because, for example, it's a bottleneck. How can I keep this task element accessing that state locally? I would need to do something with that state, otherwise I would need to go through the network to talk to that state. So in order to fix this problem, or to provide a solution for that, we introduce distributed mutable state. And we have two types of this. We have partitioned state elements, and we have partial state elements. We talk about partitioned state elements when we can access that state with a key, and we talk about partial when that's not possible, when we want, for example, random access. So I will give a little bit more of detail, actually. What is partitioned state element? Well, you can think about it as the following. You have a given state that handles a key space from 0 to n. If you are able to come up with a partitioning key k that splits that state into two disjoint partitions, so say from 0 to k and from k plus 1 to n, well, then you have state that can be easily partitioned. What do you do then? Well, you assign each of those partitions to different task elements. So that way, each task element will be still accessing only locally to its particular partition of the state. Now, when we need to send data to task element for processing, what we do is we just hash the key, and we decide on runtime which node should be handling that particular message. So if you recall from the recommender system example, you look at the user item matrix, we could say, well, the user item matrix is something that I could actually partition in this way. I could say all users with a user ID less than 1,000 will be assigned to node 1. And all those with a user ID greater than 1,000 and equals to 1,000 will be assigned to node B. So this is a naive partitioning strategy, probably, but you get the idea. And that's good, because now if we have a user that has ID 500, we will assign it to its particular node, and this node will carry on with the computation. Now, this is nice, but it's not always possible to use partition state. Sometimes I just need to access the whole state at the same time. So for that cases, we have partial state. So when we have partial state, what we do is we give each node, its physical node in our cluster, a local state instance. And what that means is that everyone will be just updating potentially updating its state independently from the others. There's no such thing such as distributed access to that state. Each one really has its own local copy of that state. And in this particular case, we have two ways of shipping data to the nodes. We can ship data in a local way. We can say, well, we have local access, which means I will only send the data to one single node. Or we have global access when we actually want to send the data to all of the nodes. Now, you can think about this case and say, well, OK, fine. But what if I'm actually reading from all of those states? So what happens in that case is something like this. You have those task elements that are accessing their partial state. We perform a global read. That means that we are reading from all of them at the same time. That would lead us to multiple partial values. So I said partial value because, well, effectively, this is not the whole value. It's just the value that one single node with in its own world is providing us. Because that probably is not meaningful for the application. What we do is we collect those partial values in one place, and then we run them through some application-specific merge logic. So maybe this is a little bit abstract. Let me try to illustrate this very quickly with an example. So let's say that we are actually counting words, and we have two different people that is counting words. And then I'm going to say, well, every word that is, 3 or 4 words, 3 or 4 letters, I will assign to this particular person. Those that are longer, I will assign to that person. So by the end, when I ask for how many times have you counted this particular word, I may get an exact answer from either one or the other, right? Because effectively, I know that each particular word has been only counted by one. But now let's imagine that I model this as partial state. So regardless who I'm sending the word, they will be counting, they will be adding that to that counter. So effectively, I have two people. Both of them have a counter for the word, say, Spain. One of them says, I've counted Spain 3 times. The other one says, I've counted Spain 1 time. So that would be this case. I perform a read, and each one tells me one answer. I will need to merge those results to get the final answer, which would be 4. So that would be a little bit about the abstraction, the stateful data flow graph. So what we've done so far is just introduce explicitly state in the data flow. And this seems nice because, well, it seems like we can model that state that we used at the beginning to represent this recommender system in a very concise way. But how do we go from that program.java, the program that I showed at the beginning, to the stateful data flow graph, to this abstraction? So this is what I'm gonna talk a little bit about now. This translation process basically occurs in 2 stages. So we have a first stage where we perform static code analysis on the Java code, and we use this to go from Java to the stateful data flow graph. And there's a second stage that we perform some bytecode rewriting to go from the stateful data flow graph to SIP, where SIP is the data parallel processing platform that we developed at Imperial College to run stateful data flow graphs. So a little bit more of detail on this translation process. Let's look at the beginning, at the first stage. So we have that program.java, we analyze that program.java, and what we do is we try to detect all the state and all the state accesses in the code. And by doing that, we then apply a number of strategies that we can use to split the code into the actual task elements. So after that first box that we have there, what we have is all the state elements in our program and all the task elements. In order to come up with the data flows, so how these are connected, we perform a live variable analysis. And this is all this does is tell us, hey, these are all the variables that you need to send to the next task element so that it can go on with the computation. So by doing that, we came up with the stateful data flow graph. And the second stage is just a lot of engineering. It's effectively saying, OK, fine, now we have this abstraction with all the code inside. I need to make this now binary compatible with SIP. So that means, in the case of a JVM-based language, rewriting the bytecode. So effectively, that means introducing new calls, introducing the new variables, etc. Bear in mind that this is completely transparent to the users. The users don't even know about this. The users really write at program.java. We provide our tools. We provide our mechanism. This compiled to the SDG. Of course, there is this new, or there is this additional piece of information that we need, which is, well, we actually don't know if those state elements should be partitioned or partial. So that's something that really depends on the application, as we've discussed before. And it is for that reason that we introduce some annotations that users can use to annotate their Java program so that we know that information. So it's effectively a way of disambiguating which type of state they want to use, they need to use. So I will go very quickly now over those annotations. In the case of the user item matrix, as we discussed, we could model that as a partition state because we can just split the user population into disjoint sets. And to do that, we just need to use the partition annotations. That's all we have to do. Then there will be a static code analysis that will parse that code and will say, well, this particular call to that or this particular access to that state has this as the key. So that's all you have to do. If you have a partial state, again, you just need to annotate the state with a partial annotation. That would be enough for us. But here, if you recall, there were these additional information that we needed, which was, are you accessing the partial state locally or globally? So are you accessing only one instance or all of them? If you don't do anything, by default, it will be accessing only one of the partial instances. If you want to access all of them, you just use the global annotations, and that's enough. And then if you recall again, what happens when we are doing a global read? Well, in that case, we wanted to collect all those partial results, merge them, and provide that result to the application. So to do that, users just need to write a merge function with a collection annotation that will trigger this barrier in the Dataflow graph. So it will then receive all those partial values from the upstream nodes. It will apply the merge logic that is implemented in that merge method, and it will provide to the users. So that would be how we go from a Java program written with mutable state to stateful Dataflow graph abstraction, how we translate it. Now, there's this missing challenge, which is, well, what does it happen when you run this on the cluster on probably tens or hundreds of machines, and there are failures? How do you provide a solution for that? So I will now briefly go over our checkpoint-based fault tolerance mechanism. So this is a physical deployment of a stateful Dataflow graph. So all those task elements are materialized in physical nodes, as I mentioned before. That means that they are running on different nodes, potentially, and they're accessing state that lives in RAM. So there are actually two challenges here. Well, if we have a failure, we are obviously going to lose the state that is kept in that RAM, so we don't want to lose the state, and we want to, therefore, checkpoint that state first and back up it to a different node so that we can recover it later. But that's really challenging. On one hand, when we are doing the checkpoint, we cannot allow to do any update to the state, because otherwise we will end up with inconsistent copies of that state. But we also don't want to stop the data processing path, because if we do that, we will have a performance hit on the effectively how the system is performing, right? And there is something similar when we are backupping that state. So backups are large. Potentially, this state that lives in memory may be very, very large. So if we want to store that on disk, that might be really slow. So how do we deal with these two challenges? So I will go very high level over the two techniques that we have for this. To perform a checkpoint, what we do is we just freeze the mutable state, and then we keep all the updates to that state in what we call dirty state. Once the checkpoint is done, we just reconcile that dirty state with the state, and that's it. We are back into normal operation. So it's really simple approach. This is really difficult to implement, but simple strategy. For backup, we do a little bit more of, it's a little bit more involved, but I will try to go over it. So say that we have this node here, which is running, and we want to back up that state. So what we do is, instead of sending it to one single node, we first partition that state into, this case, 3 chunks, and we stream them to the distributed node. So effectively, we are just harnessing the distributed performance of disks. Now, say that this node at some point fails, and we want to then recover all that state from the backup back to the operating node. Of course, if we just allocate one node and we bring all that state back to one node, we are going to have, again, a bottleneck. So what we instead do is we partition that state, so each of those nodes is going to partition its local copy of the backup, and we stream back to n nodes. So this is what we call M2N checkpoint backup. It's really similar to what projects from Stanford, such as RAM Cloud, are doing. It's really a cool technique, I think. We kind of generalize it not only for key value store, but for any kind of arbitrary state. So to wrap up the talk, I want to talk a little bit about performance. I think it's always nice to talk about performance because you present all these ideas and you say, well, yes, but how does this thing actually work? How does it perform? So I'm going to focus on these three questions, which I thought would be more interesting. So how does mutable state impact performance? How efficient are these translated stateful data flow graphs? And what is the throughput latency trade-off? So we run some experiments on Amazon, on a private cluster as well. If you have any other question about the particular settings for the experiments that I'm gonna explain now, just feel free to ask me whenever you want. So in this first experiment, we ran the recommender system that I've shown, and we wanted to understand how was these different access patterns like batch and online at the same time were affecting performance. So we have in the x-axis the workload. That's the ratio between reads and writes. That would be the ratio between add ratings and get recommendations. And what this graph shows is the throughput on one of the y-axis and the latency on the y2 axis. If I have to highlight something about this graph, is the fact that all our latencies are within half a second, most of them, some of them even in less than that. So this is actually in contrast when you think about how you would do that with batch processing platforms. So what you would usually do is you get your batch offline-oriented system, you run, you pass all your data, you compute your concurrence matrix, that might take you some minutes, even hours. Once you have this, you load it into your system that will serve that model. In this case, it's a recommender model. And then you will start providing those results. So effectively, what happens here is that, yes, of course, once you have a request, you will provide results within 1 second, let's say, within half a second. But these are results on stale data. What we are doing instead is providing fresh results within half a second. That means the result that we provide to users already incorporate all the data that the latest users have basically brought to our system. So an outcome of this graph would be to say, we can actually combine batch and online processing to set fresh results, even when we have large mutable state. So I'm talking about 30 machines in this experiment, I believe, with 10 gigabytes of state per machine. So it's a fair amount of state. The next experiment, we wanted to know how efficient were the stateful data flow graphs that we got when we were translating them. So to do that, we run this batch-oriented iterative logistic regression example where we compare with Spark, which is a system that is particularly designed to do this task. And what we find is that even when we try to move the number of nodes, the total data processed in the x-axis, and we plot the throughput in the y-axis. One nice result is we are a little bit faster than Spark. This is probably due to the fact that when you work with Spark, what Spark does is it schedules all the tasks. In our case, we instead just materialize those tasks. These are always living. We don't have any overhead. So one important thing about this graph, we are not claiming we are better than Spark. That's really not well defined. What this means is, hey, we are comparable to a system that is actually designed to do this particular task. And last, I wanted to give a little bit of details about how the system performs in terms of what's the trade-off between the latency and the throughput. So for this, we run a streaming word count query. So we are counting words over a streaming window. So we say, hey, tell me how many words you've counted every 30 minutes, or in this case, we run from 10 milliseconds to 10 seconds, as you can see in the x-axis. So we compare with Naiad. Naiad is a system that came out of Microsoft Research last year. It's been a very successful system in the research world. It's now getting picked up by Microsoft production teams. So we configured Naiad for low latency. And when I say configure Naiad for low latency, that only means trying to process as less events at a time as possible. So effectively not doing any type of batching that would introduce more latency. And what we see in the picture is that both systems, both stateful data flow graphs and Naiad configured for low latency, can achieve kind of higher throughput even with latencies as small as 10 milliseconds. We then run streaming Spark, and we then run also Naiad, but configure for high throughput. So that means configuring Naiad with larger batches, sorry, and also configuring streaming Spark. If you know about streaming Spark, what they do is a micro-batch approach where they try to just process batches, but they just make these batches really, really small. So what we see is that the throughput of both systems is constant until a given window size that requires a given latency, after which both the case of streaming Spark and Naiad goes down, which makes sense because effectively you are asking the system to give you latencies below 100 milliseconds, where actually maybe the batches are that long. So just to complete the figure, that would be it. So we can show how stateful data flow graphs can actually achieve high throughput while maintaining low latency due to our strategy of materializing all task elements in the physical nodes. So just a summary of the talk, I started arguing that it is important to find a way of democratizing big data. And by that, I mean trying to open up the interfaces, the programming language you have, so that a broader set of people can actually benefit. There's lots of people with different backgrounds that know how to ask interesting questions to the data. We just need to provide the right abstractions. So we wanted to run those Java programs with the performance of current distributed data flow frameworks. And our approach was to introduce a stateful data flow graphs that contains these distributed mutable state abstractions. We provide some annotations that we use in the translation process to disambiguate what users want to do, whether they need partitioned or partial state. And I also mentioned a little bit about the checkpoint-based fault tolerance mechanism that would allow our system to recover state when there's a failure. And that's all for now. I don't know how I'm in time, but I just wanted to leave you time enough to ask me as many questions as you want. Thank you very much. Does anybody have any question? Well, I guess that's it then. Thank you.